Yes, hello everyone. So, in this session of material science and engineering subject, we are going to learn, we are going to learn basics of phase diagram, basics of phase diagram. Okay, so before starting this topic, so let's try to observe some curve. This is pressure versus temperature curve for ice. So, how three different phases exist in case of water? So, here it will be liquid, here it will be vapor, here it will be what? Solid, that is ice. This is liquid, means water. This is vapor, means steam. So you can see here that we have only one chemical component, that is called H2O. It exists in three different phases. It exists at three different phases with different pressure and temperature combination. So from this phase diagram for water, you can see that how we have three different phases. Okay, and the reason which differentiate between two phases is called phase boundary. So this will be what? Pb is phase boundary. So this will be Pb, this will be phase boundary. So this is in brief about how a phase is developed in a component. Okay, so now slowly it is for water. What we discussed here, this is for water, H2O. Now let's try to explore and let's try to understand that what is going to happen in case of metals or alloys. Okay, so let me try. Yes, so it is very important in case of metals or alloys. So what happened? The understanding of phase diagram for alloy system is extremely important because there is a strong correlation between the microstructure and mechanical properties of a material, and the development of microstructure of any alloy is related to characteristics of its phase diagram. So what is happen? Suppose we have one metal or we have one alloy. So what happened? We have given heat to it and then we pour it in a vessel. यहाँ पे क्या होगा? This is what molten metal. Then what is going to happen? ये जब इसमें molten metal आएगा, then what is going to happen? ये धीरे धीरे ठंडा होगा, right? ये धीरे धीरे ठंडा होगा. So what will be happen? Crystallization will happen. And so during crystallization, what we observe? We will observe that phase change of material, phase change phenomena will be observed, and with phase change we will observe development of microstructures, and depending on the orientation of the microstructure, we define the mechanical properties. We can engineer the mechanical properties properties of metals. What you say, we can tune the material property of materials. So this is how if we want to improve mechanical, this is just a one property we are talking about. We are more concerned about mechanical properties, so we have to tune its microstructure, and microstructure is governed by phase change, right? But there are, as we know, there are other properties in mechanical property. What will be the mechanical properties? Such as such as fatigue. Then what? Fracture. This is similar. Then what? Creep. Then what? If we talk about chemical, so it will be corrosion or wear. So these properties we can tune in a material depending on the what? Development of microstructures. Okay, so this is the brief that what is the need of learning of this topic, that is called basics of phase diagram. So before exploring this topic, before investigating this topic, it is very essential, it is very important, it is essential to understand some basic fundamental concepts, which is like this. So let's try to understand. First we have here system. So I hope in thermodynamics we have already explored this concept, that system is area or region in space which is under observation, right? So system is referred as a specific body of a material under consideration. So suppose if we have any ladder and it is filled with molten metal. Ladder means a vessel, a component, a vessel which is filled with molten metal. So this will be what? This will be our whole system. So this is what? Molten metal. Okay, so this is what? Molten metal. Now another term is called component. So a component is the one of which the system is composed of. So let's take one example. Let's brass. Brass is combination of copper plus zinc. So here brass is our system which is under observation, and here it is composed of what? Copper and zinc. This is the component. So here we have two component. So this is our component, copper and zinc is the component. Okay, so if we take ice water vapor system, in this ice water and vapor system, here our component will be only one, because it have only one chemical composition, right? H2O. Here component will be one. It is all composed of H2O, but here in this case you can see copper and zinc are two different elements, right? So here a component can be either element or compound. Component can be either element or compound, right? So this is one point. Another point is phase. Another point is phase. This is the very important definition. So let's try to understood in different page. So the third point is phase. Phase, a chemically homogeneous a chemically homogeneous, physically distinct, and mechanically separable part of a system. Part of a system is called phase. Is called a phase. So in case of that first page we have learned that solid, liquid, and gas, these are three different phases of a matter. These are three different phases of a matter. So let's try to understand solid phase. Solid phase. So if we have different crystal structure, if we have different crystal structure, different crystal structure will be considered different phases, and traditionally these phases are shown by Greek letters. These phases are shown by Greek letters. So if we see iron at room temperature, we call it as alpha iron, and this is BCC in nature, right? But at higher temperature, iron at high temperature, it becomes what? Gamma iron, and it converted to FCC. So this is BCC crystal structure, and this is this is BCC crystal structure, this is FCC crystal structure, right? Both are pure iron, both form are pure iron. In terms of chemical composition, they are not different because they are made up of iron, right? They both are crystalline solid. They both are crystalline solid, crystalline solid, but their crystal structures are different. But their crystal structures are but their crystal structures are different. So they are considered as different phases from the point of view of phase diagram. So they are considered as different phases. So we will discuss its phase diagram in future lectures. So from here you can see that phase is a chemically homogeneous, physically distinct and mechanically separable part of a system is called phase, right? So here we have two different phases. It is chemically homogeneous and physically distinct, right? So these are two phases of iron. Okay, so this is about uh, what of phase. So let's try to explore some other concepts. Now let's try. So let's try to understand what is let's try to understand how we define system components and phases. So in case of, let's take example 1. In case of water, right? In case of water is a single phase system, right? So here component will be what? H2O. It is fixed composition. It is fixed composition. It is the fixed composition of hydrogen and oxygen, and phase is what? It is liquid. Okay, now let's take another example. Water plus ice. So you can see here here we have single component. So component is what? H2O. In this component will be H2O, and what phases will be there? Liquid plus solid. Okay, so let's take third is brine. Brine means what? We take water and we mix NaCl in this, so it will become brine. So in brine we have two component, NaCl plus H2O. So this will be what? Phases will be what? So here it will be single liquid phase. Here it will be in single liquid phase. So यहाँ पे क्या होगा? What is going to happen here? NaCl will completely dissolve in H2O and it will form single liquid phase. Okay, and let's explore more. Mild steel at room temperature. So here we have in case of components we have iron and carbon. We will have two components, and what phases will be there? We have alpha phase and Fe3C phase. So these things we will explore in future. So I hope it should be up to this, it should be clear to you how we define system, how we define components, how we define phases. In water we have single H2O fixed composition of component, and its phase is what, liquid. In water plus ice, the component is H2O, and phases is what, liquid plus solid. And in brine, components are NaCl and H2O, and this will be what, single liquid phase. But single liquid phase. And in fourth we have mild steel. At room temperature we will, the components will be iron and carbon, and here phases will be what, alpha and Fe3C. This is called cementite, this is called alpha iron what, ferrite. We will explore it soon. Okay, so from here, let's explore some more concepts. uh, so another concept is here, the concept of solid. The concept of solid solubility limit. So what you do, take one glass of water, and you put first one spoon of NaCl. NaCl is what, namak. So what is going to happen? So you just put one spoon of NaCl and then stir it. Okay, so what is going to happen, NaCl will dissolve in the liquid. Okay, then you put another uh, tablespoon of NaCl in this, so it will be dissolved in this. Now you put 1 kg of salt. Now 1 kg of salt in what, in 1 glass of water. So what is going to happen, that 1 kg of salt, it will, let's suppose it is completely dissolved in water. Now as you increasing the amount of salt in a water, let's take 1.1 kg. Now this water will say, bro, don't mix much more amount of salt inside me. Now I am saturated. Now I can't accommodate any more amount of NaCl within myself. So here this NaCl will be what, solute, and here water will act as solvent. So from here we define the solid solubility limit. Solid solubility limit is what, the maximum concentration solid solubility limit is the maximum concentration of solute atom which may dissolve in solvent to form a solid solution is called solubility limit or solubility limit. So this is what, solubility limit. So maximum amount of solid atoms which can be dissolved in solvent, that is called solubility limit. So what is going to happen, and when this solubility limit so what is going to happen, whenever the concentration of solute atoms goes beyond the solubility limit, then excessive solute forms either another compound, or then it will form another compound, or another solid solution, which property will be entirely different property. which properties will be entirely different property. So this is the brief concept about solid solubility limit. So these things we will needed in future classes, in further classes. So let's explore. So let's let's explore more. So now this is the first time we are going to explore. Not first, let's explain one component system. One component system, or it is called unary phase diagram. So here it will be what? Ice, water, vapor system. So I hope we have already learned in the first page of this lecture, but let's try to sequentially understand how we define unary phase diagram. This is unary, then in future we will get different binary and ternary phase diagram. So let's first try to understand this. So it is simple as we have earlier discussed. So in unary phase diagram, so it will be what? Component value will be 1. It is single component. So what is going to happen? So this is right, this is water, this region is vapor, this region is solid, and this is pressure, this is temperature. So here we have 3 phases, and this point is called what? Triple point. Triple point, this will be what? Ice, this will be liquid, and this will be what? Steam. So these are the 3 different phases in water as a component. So here if we measure the degree of freedom from the Gibbs phase rule, we use formula P plus C equals to C plus 2, right? And this formula changes into P plus F equals to C plus 1 when pressure is fixed, right? So from here we can calculate degree of freedom at different locations. So you can calculate. So in this region, you will get degree of freedom on this curve. Degree of freedom will be 1. On this curve, degree of freedom will be 1. And in this region, degree of freedom will be what? 2. And at this region, degree of freedom will be 0. Okay, and at this region degree of freedom will be what? 1. So these are the different reasons where degree of freedoms are defined. Now let's explore more concepts. So let's try to understand phase diagram of copper nickel system. This is a copper nickel system. This is also called binary isomorphous system. Iso means same, morphous means structure. So copper is having FCC and nickel is having FCC crystal structure. That's why this is also called binary isomorphous system. So we have earlier that this copper and nickel system, they follow the Hume-Rothery rule, and they make a solid solubility, and they make solid solution with substitutional solid solution of copper and nickel. Okay, so let's try to understand and let's try to learn how its phase diagram is generated, how its phase diagram are formed. So here we have one axis. So here we have temperature, right, and here we have melting point of copper. This is around 1085 degrees Celsius, and here this is also temperature, and here we have what, melting temperature of nickel. It is around 1453 degrees Celsius. Okay, and here we have on x-axis we have 100% copper, and here we have what, 100% nickel. So this is pure nickel and this is pure copper. Okay, now tell me one thing. So at this point, what phases will exist? So I think you can understand from here, if the temperature will be less than melting point of the copper, then here we get solid phase, and as we increase the temperature above melting point of copper, we will get which phase? Yeah, liquid phase, right? And in case of here on this side we have 100% of nickel. So if temperature is below T melting, we have solid phase, and if we have temperature above T melting, we will get liquid phase. Okay, so this is called one dimensional phase diagram. Here and here, this is called what, one dimensional phase diagram. Now guys, can you tell me at this location at T melting, what phases we will get? What phases we will get at T melting? We will get solid plus liquid phases in equilibrium. So this is like thermodynamic equilibrium. What does this means? That there is the derivative of any quantity with respect to time will be zero. So no amount of solid will change into liquid, and liquid will change into solid. So this will be in equilibrium at this melting temperature. Okay, so now what we are doing here, we have this copper as a solvent, and we are increasing the nickel composition here. Nickel composition here, so we write is weight percent of nickel. So we are adding nickel here. Okay, so here nickel will be increased. So can you tell me what will be the weight percent of nickel here? So it will be what, 0 weight percent of nickel. Okay, So can you tell me what will be the weight percent of copper here? Here it 100%, so here it will be 0% copper. Okay, as we go from this side to this side. Now these are the melting point for pure copper and for pure nickel. Now what uh, our aim, let's try to identify what will be the melting temperature for 50 weight percent. This is 50 for 50 weight percent of nickel. At that line, what will be the melting temperature of that alloy? So what is going to happen? Let's try to connect with this or dotted line. Right, so from interpolation, so from interpolation we will get this point. So can we say that this point, this temperature is the melting point of the alloy comprising 50 weight percent of copper and 50 weight percent of nickel? Ideally, it looks like what it looks like that its melting temperature will be here for alloy, but experimentally it was not observed. Experimentally it was not observed. In case of alloys, melting happens over a range of temperature. So melting happens over a range of temperature. So let's try to draw experimental results. So in case of alloys, melting happens over a range of temperature. Okay, so this region, let's close this. So this region will be liquid, this region will be solid, and this region will be solid, this region will be liquid. Liquid we denote it by L, and solid we denote it by alpha. As we have learned earlier that solid phases are denoted by Greek letters. Okay, so if this is liquid, this is solid, so can you imagine that this will be what? Alpha plus liquid, right? So the boundary line between liquid and this zone is called mushy zone. So we write here, here we have alpha plus L, so we write as two phase mushy region. Two phase mushy region, right? So the line between liquid and this mushy region is called liquidus line. This is called liquidus line, and this is called solidus line. The line separating, the line acting as a boundary between solid phase and this mushy region, its spelling is MUSHY, right? So these are the important point in phase diagram of copper nickel system, that is called binary isomorph system. So in next PPT we will learn how we draw different microstructure when we cool a liquid for a fixed composition, and if we are cooling the sample from liquid to this mushy zone to solid phase. Okay, So this presentation is all about this. Now let's explore more how the different phase diagrams, how the microstructures evolve during the phase transition. So okay. Development of microstructure in isomorphous phase diagram. So first draw that isomorphous phase diagram. So this is one point, this is another point, so it will go like this, it will go from here like this. Okay, now take one point, suppose at some fixed concentration. So this section is our copper 100% copper, and here we have nickel 100% nickel. This copper is having FCC crystal structure, nickel is also having FCC crystal structure. Okay, so now let's see, at this fixed particular concentration we draw a vertical line. Okay, now let's take so let's take the point A. Let's take point A here, B here, point C here, point D here, point E here. So you can see at A at A at A we have liquid phase, so it will be like this. It will be liquid state. Okay, and at point B what is going to happen? So here we have this region, अरे यार इसको क्यों पकड़ लिया भाई? You want only this. Just 1 minute guys, let me shift it here. Okay, so in at position B, so what is going to happen, we will be having this liquid phase, because this is in mushy zone, and we have alpha plus what, this is L, this is alpha plus L, this is alpha region, that is solid region. तो यार यहाँ पे क्या होगा, here nucleation will start, here nucleation will start, here nucleation will start. Okay, so let's see what is happening at point C. At point C we have we will still having liquid phase here. Okay, we will having liquid phase here. So guys, I hope you can see from here we have point A, B, C, D, E, and we are going to draw what is the microstructure at different point. So at location 1 we have only liquid state, because this point is present in liquid, so we will draw a lot of liquid points. As we come down on this line, we will enter in the mushy region. This is what mushy zone. Okay, in this mushy zone what is going to happen, a nucleation of solid phase, that alpha phase will start, that nucleation of alpha phase will start. Okay, and at point C this nucleation will grow slowly, and at point D the nucleation it will actually grow slowly. So nucleation front will grow slowly. Okay, and liquid phases will be present, but at point E and below this point E we will get what, grains of alpha phase, we will get grains of alpha phase, and the grain boundary which will be present between two grains, right? Grains are having different orientation, you can see this is another orientation, this region is oriented in another way, right? So E phase is defined as a single phase of polycrystalline structure. Okay, so this is all about development of microstructure in isomorphous phase diagram. Okay, so some important observation from here, and if we are cooling the molten metal, if the that slow cooling, if we have slow cooling, so grain size will be coarser grain, so we get coarser grain, right? And this coarse grain are less corrosion resistance. So what is going to happen in this case, the material will corrode very easily and very fast manner. Okay, and if we do a fast cooling, we will form a fine grain, we will get a fine grain, right? And this will be having high high corrosion resistance. So this will be having high corrosion resistance. But in case of fine grain, the material will be having high strength and toughness value. Material will be having high strength, high tensile strength and toughness value. That's why what we need in our engineering material, that it should have fine grain, so that it should having high corrosion resistance value, and it should have what high strength and high toughness. So this is all for this lecture. And this grain boundaries will be like this, guys. So I hope this is all.